Okay, thank you. So last time we discussed the basic ideas of the MMP. So I introduced some notions of singularities and the main steps of MMP. So in this lecture, first I would like to make some remarks and extensions, and then try to translate the notions that we've seen yesterday to the world of foliations. So some remarks and extensions. So the first remark is about length of extremal rays. So let me remind you that in the cone theorem, we saw that on the negative part of the cone, where k is negative, the kx negative, let's say in the case x smooth, so the k negative extremal rays were of the form, were generated by rational curves C with anticanonical degree bounded by the dimension +1. So let's say smooth of dimension n, well, let's say here this is dimension x +1. And let me remind you that in the surface case, so when the dimension of x is 2, then so the possibilities for C, for the anticanonical degree of C, were then it's 1, 2, and 3. And this corresponds precisely to the case when the C is, well, if the anticanonical degree is 1, then the C is a -1 curve. If the anticanonical degree was 2, so this corresponds to F, C was a fiber of a ruled surface. And the case when the anticanonical degree was 3, the C was a line on a P2. So we see that when the length of the extremal ray is maximal, we have projective space. The middle case, we have a fibration and then a -1 curve. So a similar classification holds in arbitrary dimensions. So for dimensions n greater or equal than 3, again, so let me say this is not a trivial result, but it follows from a theorem of Shaw, Miyaoka, Scheffer-Baron, reworked by Quebecus. That again, the largest extremal ray can only occur for Pn. So if the length of the extremal ray, so we call this the length of the ray. Well, we call the length of the ray the minimal value of the anticanonical degree for any curve in the ray. So if the length is equal to n + 1, if and only if X is isomorphic to a projective space. And again, well, I'm not going to state this. I think this is the only one that we will need in the lecture tomorrow. But if, for instance, if I know that the corresponding contraction is birational, then this length can be at most n minus 1, exactly as we see here. So, and in some of the cases, there is a classification. Okay, so this is about the lengths of extremal rays. Now, let me tell you something. Related results about Fano manifolds. So these are, say, we are in the smooth case. So these are smooth projective varieties when the anticanonical class is ample. So when I have a Fano manifold, we can measure the positivity of the anticanonical by means of, say, the index. This is one way of measuring the positivity. So this is the maximal integer such that minus k is E I times A, where A is some ample line bundle. So here, again, there is a theorem that bounds the index of a Fano manifold. So the index cannot be arbitrarily large. So once I fix the dimension, this is bounded. So the theorem, so this is Kobayashi-Oshai. So I think this is from 73, and it says that if you have a Fano manifold of dimension, so X, Fano manifold of dimension n, then the index, so the first part of the statement says that the index of the Fano manifold is bounded by n plus 1. Of course, this bound is achieved for Pn. So for P, the canonical class of Pn is n plus 1 times the hyperplane section. But in fact, this is an if and only if. So an equality holds if and only if X is Pn. And they also classify the next case. So the index of X is equal to n if and only if X is isomorphic to a quadric hypersurface in Pn plus 1. So these are the Fano manifolds with highest index. So we see that this is a stronger form of that statement. So of course, if the index is at least n plus 1, then so is the length of any extremal ray. Okay, so this story continues. So if you look now at Fano manifolds with index n minus 1, these are called the Del Peso manifolds, and they were classified by Fujita. And the next case, if the index is n minus 2, they were classified by Mukai. So there is a, so this is all in the smooth setting. There are some results in the singular setting as well, but I don't want to get into this. So. So the theory of Fano manifolds is very well developed, and I don't want to say much about it, but I cannot avoid to tell you at least some of the most important properties of Fano manifolds, and this is So this is sort of one of the most important geometric property of Fano manifolds is that they contain many rational curves. So they are what we call rationally connected. So this is a theorem that was proved independently by Campana and Kolar, Miyaoka, and Mori. So Fano manifolds are rationally connected. So this means that if I take any 2 points, x and y, on a Fano manifold, one can find a rational curve connecting them. And the theory of rational curves becomes a very powerful tool to study these manifolds. And this theory of rational curves, for instance, can be applied to prove these results that I mentioned. And we are going to see some of it tomorrow. So before I move on to the next topic, let me just anticipate what we are going to prove tomorrow. So tomorrow, I want to prove a version of Kobayashi-Oshai for foliations. So Kobayashi-Oshai for foliations. So let me state it. So if you have, so this we're going to see tomorrow, if you have F, a Fano foliation on, say, a smooth projective variety, X, let's say, let me just make, let's say, with rank, I want to avoid the trivial case when the foliation F is X itself. It's the tangent bundle of X itself. So let me assume that the rank is less than the dimension of X. Then in this case, we prove that the index, which is defined in the same way as I defined the index of a Fano manifold, is bounded by the rank. And equality holds if and only if X is Pn and F is induced by a linear projection. So that means that it is, you fix a P r minus 1 inside a Pn, and you look at all a linear PR minus 1, and then you look at all linear PRs that contain this fixed PR minus 1. So this is the foliation. So this is the goal of these lectures, and today we're going to introduce the tools that we need to prove this result. Some tools that we need to prove this result. So some of the tools are the ones that I introduced yesterday, the MMP. We're going to run MMP in some context here, and now I will move on to prove to introduce some other tools that we need. Okay, so this was for Fano manifolds and Kobayashi-Oshai for foliations. And now I need to introduce some notion that has already appeared in some of the talks, which is the notion of a log pair. So the idea is the following. So yesterday we started with, say, a smooth projective variety, and we considered the canonical class, and this governed the MMP for X. And we saw that we had to, in order for the program to work, we had to allow some singularities on X, namely, I told you that terminal singularities were the minimal set of singularities that we have to allow in order for the program to work. Now, a log pair, we are going to extend this to the following setting. Instead of considering a variety as a projective variety X, we are going to consider a pair, X delta. So the X is going to be a normal projective variety. And the delta, well, you can put some restrictions on that or define it in more general, but say for me, this is going to be a Q divisor, an effective Q divisor. In some contexts, you can allow it to not to be effective and even be R divisors, but let's say for our purposes, these are effective Q divisors. And just like in this case here, even if I always assume that the Kx has to be at least Q Cartier, so that I could run MMP. Here I will require, instead of looking to Kx, we are going to look at Kx plus delta, say as a Q divisor. And we always require that this is Q Cartier. So this is what I call a log pair. A normal projective variety and an effective Q divisor satisfying this property. And the idea is that for instance, we want to run, when we introduced MMP, we measured, we asked for niffness, and we measured intersections with respect to Kx. We can do everything replacing Kx with Kx plus delta. And these pairs that may look a bit artificial, but they appear, so log pairs appear naturally in many contexts. So let me just mention a few of them. So it already appeared in Demail's talk on Monday. And it appears naturally, for instance, if you want to work with non-complete varieties. Suppose you want to study geometric properties of non-complete varieties. One way to proceed is to compactify it into a variety X by adding some simple normal cross and divisor, and then working with X. So this will have a canonical class, and then you can ask for numerical properties of this canonical class. Now, if you change the compactification here, you will change the canonical class, and the properties can be very different. But if you keep track here of the boundary, so this is, say, X naught union a simple normal cross and divisor, and if you look at Kx plus delta, this is much better behaved. Then it will not depend so much on the compactification as long as you take normal cross and divisor. So this is one instance where it appears. It also appears, even if you're interested in a minimal model program, not for pairs, but just for varieties, you have to consider pairs because they appear in the inductive scheme of the proof of MMP. So in which sense? So let me recall you that if you look at the adjunction formula, so if you have, say, a y inside of X, a smooth hypersurface, then in order to describe the canonical class of Y in terms of X, you restrict not only not the canonical class of X, but the canonical class of X plus Y. So this is the adjunction formula. And so the proof of MMP runs induction on the dimension. And so in this sense, when you run induction and you restrict to a subvariety, you see that a pair naturally occurs here. And there are many instances where it occurs, and what we will see now next is that for when you study algebraically integrable foliations, we naturally get a log pair associated to F. So we will see that whenever you have an algebraically integrable foliation, we can associate a pair F delta that I will define in a few minutes. Okay, so this is just to motivate this the introduction of this object. And just like I introduced some notions of singularities for a variety X that appear naturally in the minimal model program, we can do the same with pairs. So let me define the important notions. So let X delta be a log pair, and F tilde from X tilde to X a log resolution. So that means that this is a projective birational morphism. And here, the log means that if I look at the exceptional divisor of F tilde, union the support of the strict transform of delta, this is simple normal crossing. Okay, so once I have this, I can do the same thing I did yesterday. I can compare, say, the canonical class Kx tilde, let's say, plus delta, with the pullback of the log canonical class of X. So this is the pullback of Kx plus delta. And I say that, okay, then plus, and there is going to be a sum over exceptional divisors, prime exceptional divisors of say AE dot E. And so this A, E are going to be rational numbers. Again, I write this, at least this over Q. So I require that this is Q Cartier. So after multiplying by some integer, I can take pullback, and then I can write this expression. And then we say that the pair X delta is, well, I will introduce here. So there are some notions that I already introduced last time. So terminal, canonical, and now I will introduce KLT, which stands for Kawamata log terminal and log canonical. If all the AEs are say greater than 0, greater or equal than 0, and then here greater than -1, greater than equal than -1. I think probably for the, we will be interested in this class of variety. So probably in the KLT case, I also want to require, so maybe in the KLT case, I also want to require that the round down is 0. But this is not going to be so important for us. So you can think of this, it may look strange, but in this case here, for the log canonical, you can think that I can increase my boundary divisor delta by adding one copy of each prime divisor, and this would then ask that if I put it to the other side, that these coefficients here are greater or equal than 0. So this would be the log version of the canonical singularities, and these are natural. This is a natural condition to ask. So let me just remark, and if you're not used to that, I don't expect that you are going to grasp this definition so quickly, but let me just tell you the example that you should keep in mind, and this is the example that this is everything that we are going to need. The most important example is the case of a smooth variety together with a simple normal crossing divisor. So if you take X, a smooth projective variety, and delta, a simple normal crossing divisor on X, then X delta is log canonical. On the other hand, if you increase a little bit the coefficients of delta, if any coefficient is bigger than 1, then it's automatically not log canonical anymore. And in a sense, you can think of log canonical singularities are the ones that appear if I run the log minimal model program starting with a simple normal crossing pair like this. Okay, so, and let me just remark that the MMP with scaling that I explained yesterday works in the greater generality of a log pair with KLT singularities. So MMP with scaling, as in BCHM, works for pairs KLT. Well, in the two cases when, as last time, when Kx plus delta is either big or not psif. And when I said MMP, MMP in this case is whenever we saw Kx, we replace Kx by Kx plus delta. And in fact, it works even in a stronger sense. Here we can replace KLT by DLT. I don't want to introduce more notation, but DLT is something in between KLT and log canonical. And log canonical is the biggest class of singularities for which one can hope to have an MMP. So it is conjectured that we can run MMP in the log canonical case as well, but this is not known. Okay, so this is all the remarks and extensions in the case of varieties, and now we move to foliations, and we are going to introduce similar notions of singularities for foliations. Okay, so let's start. So now foliations. So we start, we are going to work on the smooth context, where the ambient space is smooth. So this is a smooth projective variety. And F is a foliation on X. So the first thing that I want to introduce is Macquillan's analogs of these notions of singularities for pairs to foliations. So definition, so this was introduced by Macquillan. So if you have, we take a resolution. So a resolution of, in fact, X is smooth. So this is, say, any, we take any birational morphism, let's say with X prime smooth. And again, as I said in my first lecture, if you have a foliation on X, there is a unique way to obtain a birationally equivalent foliation on X tilde. You just look at the open subset. There is an isomorphism. You take the F in this open subset, and then you extend it in the unique saturated way. So now we want to compare the canonical class of F tilde in X tilde with that of X. So as usual, they will differ by some exceptional divisors. Prime exceptional divisor. So in the exception of F of some AE. So we have an expression of this form, and we say that, well, we can introduce similar notions. As I said, we are going to be interested in the log canonical case, so I will define only this one here. And for that, let me introduce the condition that we are going to ask on the AE will depend on whether or not this E is invariant with respect to F tilde. So first we define the E of E to be, so this is going to be 0 if E is invariant by F tilde. And by that, I mean that it is, if it is a union of leaves. And we say that it is 1 if E is not invariant by F. And the condition here that we want is that we say that F is log canonical if for every such morphism, birational morphism F, and for every prime exceptional divisor, the AE that appears there is greater or equal than minus E of E. So this can look a bit strange, and one has to contemplate this a little bit to see why you require something stronger for invariant divisors. But I will. But let me tell you what this means in the very special case of algebraically integrable foliation. So let's look at this condition for algebraically integrable foliations. And in this case, this condition has a very natural interpretation in terms of the log pair that is naturally attached to such foliation. So let's fix notation here. So again, X is a smooth projective variety. And say F, an algebraically integrable, so I will abbreviate it by AI. So this is an algebraically integrable foliation on X. And so that means that the leaves are algebraic. So let me call F the closure of a general leaf. So this is a irreducible closed subset of X. So this is the closure of a general leaf. And now comes the natural log pair that we can associate to F. So then the claim definition is the following. There is a naturally defined Veil divisor. Maybe I want to work on the normalization. Let's say take a closure of a general leaf, and let me call F tilde to F the normalization. So now on the normalization, there is a naturally defined Veil divisor, delta, such that the Kf tilde plus delta is the pullback under the normalization of the canonical class of the foliation. So notice that this F, we have no control on this F tilde. It is a normal variety, but it may not be Q factorial. It can be very singular. And so we don't even know if the canonical class of F tilde is Q Cartier. But once we add this natural divisor, this becomes actually a Cartier divisor. Okay, so let me I forgot to actually give you the definition. So the definition is that we say that F tilde delta, so this log pair, is the general log leaf of the foliation. Okay, so let me quickly tell you why. So this is very easy to show that it exists and it's natural. So if you have a foliation, so the proof, if you have a foliation on X, so we have this inclusion of sheaves. So what I can do is I can take wedge R. R is the rank of the foliation, and then dualize it. And then what I get is the omega Rx mapping to the, then there I get the canonical class of the foliation, or the anticanonical class, probably. Oh no, I dualize, so I get this. And now I can restrict this to the closure of the fiber. And because it is a closure of the fiber, it is invariant, and this means exactly that we have a factorization like this. And then this extends to the normalization. So after you take the normalization, what you get is the omega r of f tilde mapping to the pullback of kf. And this is a generically surjective map. And so there is a naturally defined delta that makes, so this says that there exists a sort of a unique effective divisor delta, or naturally defined delta, such that kf tilde is plus delta is the pullback of kf. And as we will see, this log leaf plays a very important role in the study of algebraically integrable foliation. So let me just tell you some facts. So for instance, if you look at McQuillan's definition of log canonical foliation, then in the context of algebraically integrable foliations, this implies that the general log leaf is log canonical. So, so if f is log canonical in the sense of McQuillan, then the general log leaf is log canonical. In the sense of log pairs. So this is the first fact. This is not difficult to check. And also, let me tell you something about this delta. So this delta consists exactly of the points that are in the closure of an infinite number of leaves. So the support of delta is precisely consists of the points such that, so the image in X is in the closure of infinitely many leaves. It is in the closure of a positive dimensional family of leaves. So let me give you some examples. Sorry. I started with fixing a general leaf. The F is a general leaf, and then I take the normalization. Otherwise, this may not be true. Okay, so let me give you a few examples. So let me start with some easy examples. So let's start with let's start with X is Pn, and let's consider a linear projection. So I take this F is going to be some direct sum of O1s in Tx. Here, this R is smaller than n. So this foliation here, as I said, is it's given by the linear projection, so I fix PR minus 1, and I look at the linear PRs that contain this fixed PR minus 1. So in this case, the F itself is isomorphic to PR. And the delta, so in this case here, what is the canonical? We can easily compute the canonical of, or the anticanonical of F is going to be O Pn to the R. The fiber, the closure of the leaf is PR. The delta here, at least the support of delta is precisely this linear PR minus 1. So this corresponds to a linear, let's say, V PR minus 1. And now if you look at the adjunction formula, so we know that Kf plus delta, it has to be the pullback, or in this case, the restriction of Kf. And if you compute, you will see that, in fact, this delta is reduced. It's the V itself. So the F delta is PR with a linear PR minus 1. And notice that we see that in this case, for every point here in the delta, so the delta, the image of the delta is the same for every leaf. So every leaf passed through a point here. So this or the closure of every leaf. So this point lies in the closure of every leaf. Now, this need not be always the case, so let me give you a couple more examples. So this is in particular, this is a foliation. And now the next case, let me take X to be, say, P2 cross P2. So it will have two projections. And in each projection, I can consider a linear foliation like this, degree 0 foliation. So I do this for the two projections, and then I consider the foliation. So let me call this G in each case. And I take the foliation F to be pullback of G1 plus pullback of G2. So this is a rank 2 foliation on X. And we see that the leaves are going to be the product of the leaves. So the F is a P1 cross P1. And we see that the delta is supported precisely in the union of the inverse image of these two singular points. So the delta in this case is a union of each of the rulings. So that at least at first it is supported that, and then you actually compute that it's here. So the delta, so this is going to be a fiber, a union, let's say, F1 union F2, the fibers. And now if you compute the canonical of the foliation and the canonical of the leaf, and you apply the adjunction formula, this adjunction formula, then you get that in this case, actually, again, the delta is reduced. So the F delta in this case is P1 cross P1, and the delta is given by a union of fibers. And then again, you see that for points, now there are two different behaviors. If you take a point, general points on these two components, then through those points, you get so they are contained, each of these points is contained in a one-dimensional family of leaves, while this intersection point here is in the closure of every leaf. So it's in the closure of every leaf. And now let me give you a last example. So this is, I'm going to start, so let me start again easily with a linear projection from a point. So I take a point in Pn, and I consider the linear projection to Pn minus 1. Now I will look at the induced map on the Grassmannian of lines. So this induces a map from the Grassmannian of lines in Pn to the Grassmannian of lines in Pn minus 1. So the inverse image here, if you look at a line on Pn, then the inverse image, so if you look at the inverse image of this line, you're going to get a P2. And any line that lies in this P2 and does not pass through the point P is mapped to that line. So we see that the fibers here, so the fibers are P2, the P2 of lines in this plane, minus the linear P1 of lines passing through P. So this rational map induces a foliation on the Grassmannian. So this is our G, this is our X, and the foliation is the foliation induced by this linear map. And so in this case, what do we have? We have that then the F, the closure of the leaf is isomorphic to P2. The support of the delta is going to correspond to a linear P1, L, line. So let me write line. But now, if you use the adjunction formula to compute the coefficient of delta, so we see that the canonical of the foliation is, or the anticanonical of the foliation is precisely the O1. Here is the hyperplane given by the Plucker embedding. So you just compute the relative canonical class of this map. And then if you plug in here, you will see that in the adjunction formula, you will see that actually in this case, the delta, the F and L is P2 with 2 times a line. So here, in all the other cases, this is log canonical. The same thing here. This is log canonical. And in this case here, this is not log canonical. And all the foliations that I defined are funnel. So this is a funnel foliation. And now we see a different behavior here in this case. So as always, a general point on the delta is in the closure of infinitely many leaves. But if I take here n greater or equal than 4, so what is the closure of a leaf? This is going to correspond to the P2 of lines in some Pichu through this point. If I take two Pichus that do not have any line in common, then that means that those leaves or the closure of the leaves do not intersect. So if I take n at least 4, then there is no common point. There is no point in the closure of a general leaf. So there is no point that is contained in the closure of every leaf. And this is not an accident, so let me end by stating a theorem or and this is going to be a key point in the proof of the Kobayashi-Schiffer for foliations. So proposition. So let's say that we have X, smooth projective variety, and F, let's say a non-trivial. Let me rule out the trivial case of F being Tx. A phonofoliation so if the general log leaf F tilde delta is log canonical, then there is a common point in the closure of a general leaf. So I'm not going to give a proof, but let me just say that this is this is a consequence of a theorem that does not involve foliations. We look at the space of in the family over Schau, parametrizing leaves, and in a sense we use we use positivity of the push forward of the canonical shift. But I don't want to get into the details because I don't have time for that. So I will just stop here, and then tomorrow we put in all these tools together. We prove Kobayashi-Schiffer. Thank you.